Hello everyone, and thank you for joining me. My name is Evan, and today I'll discuss a recent work titled Guiding Neural Collapse, Optimizing Towards the Nearest Simplex Equiangular Tight Frame. This work was done in collaboration with Thalaiyasingam, Ajanthan and Gould. Neural collapse is a phenomenon observed in the later training stages where neural networks align class features and classifier weights into a symmetric configuration. As illustrated here, class features converge to their means while classifier weights align in a dual space, forming an optimal arrangement known as the Simplex Equiangular Tight Frame, or Simplex ETF. This configuration maximizes class separation, enhancing generalization and robustness, and stabilizing training dynamics. Existing methods face challenges with neural collapse in practical applications. For instance, allowing convergence to an ETF solely through gradient descent can be slow, and fixing a classifier to a predefined ETF doesn't significantly speed up training. We therefore need a method to accelerate convergence to a neural collapse solution. Given that an ETF solution is rotation and permutation invariant, we ask the following question: can we leverage these invariances to guide the network towards the nearest Simplex ETF? By leveraging ETF structure, we propose the method to accelerate neural collapse convergence by continuously guiding features towards the nearest Simplex ETF. We formulate this problem as a Riemannian optimization task, and we use theories from deep declarative networks for efficient backpropagation. Our method shows faster convergence and improves training stability across various classification tasks. In standard training, the network learns both the features H and the classifier weights W. However, in our approach, classifier weights implicitly depend on the feature means. More specifically, we compute the normalized per class means of the backbone features, we identify the nearest Simplex ETF to these means, and we use it as the classifier update at each gradient step. This approach provides a structure for the network to aim for, guiding it towards the neural collapse configuration. Mathematically, this translates to a Riemannian optimization problem over a Stiefel manifold, where we find the closest Simplex ETF to feature means under a Frobenius distance. Furthermore, adding a proximal component ensures uniqueness and training stability, guiding our problem towards progressively stable solutions. We incorporate Riemannian optimization into a deep declarative network, enabling end-to-end training with implicit differentiation. This approach stabilizes training through an added gradient stream. We derived the gradient analytically as shown in this expression. For further details and analysis, please refer to our paper. In synthetic tasks across different UFM sizes, our method, shown in purple here, achieved fast convergence, while the fixed ETF in green and standard training in blue required more iterations to reach the same level of performance. On the imaging dataset, our approach shows faster and more stable convergence, notably in training accuracy in plot A and test accuracy in plot G, outperforming the other methods. The rest of the neural collapse convergence metrics are explained in our paper. In summary, we introduced a method to dynamically guide networks towards the nearest neural collapse solution. We enabled efficient gradient computation with a declarative node. And we also demonstrated that this approach results in faster convergence and improved stability. Finally, as a takeaway message, we emphasize that aligning features with the nearest Simplex ETF significantly enhances neural network training. Thank you for your attention.